Okay, the second part of this is I want to just do a little bit of graphing and directions with you. Because this, again, this is a misconception that some students have. So we'll start off very basically and look at two dimensions. So I'm going to draw an axis, something like this. And this is going to be your simple everyday number line. Let's just call this point here the beginning. We won't have a negative in this case. So we'll call this 0 meters. This is a 0 meter mark. And what I want to do for convenience sake is I want to just group this so it becomes one item. There we go. Now, what I want to do, and maybe some of you already have an idea what I'm going to do, is I'm going to simply put ticks here every centimeter and give it an appropriate scale. So we'll just call this 1, 2, 3, 4, 5, 6, 7, and 8. Alright? So, just as we've done before, if this happens to be my position axis, then if I start at home or at 0 and I go to here, for example, then I've gone 5 meters, and of course it is a vector, so let's just call it, for the sake of argument, east. So I think we agree this direction is east, so I've gone 5 centimeters to the east. Fair enough? Now, when constructing a graph in 2 dimensions, our other quantity we often want is time. We want to know where we are at a certain period of time, and that can give us some indication as to how fast we've gone, how fast we're going, and so on. So, in order to make this into a Cartesian plane or 2 dimensions, what I want to do is I want to take this axis, let's just undo that movement. I want to take this axis like this. Of course, now it wants to, and I'm going to simply flip it around. It's going to go up 20 here. So let's just rotate that around, like so. And now what that has become is our vertical axis. And just like before, it's still position. And even though it's pointing up the page, it's still east. Let's just ungroup that for a moment, and we'll just delete that. We don't need that there. So what you see here is you see a number line that was lying flat when east, and now we've just simply rotated it so it becomes the vertical axis. So once again, we have our positions. There's 0, 1, 2, 3, 4, 5, and we'll say 6. 1, 2, 3, 4, 5, 6. And this axis, I can put it in, and I will simply call it my time axis by units of seconds, and let's give units there of meters. Now I can say that at, make it simple, at 1 meter, or 1 second, I was at the 1 meter mark. Maybe at 2 seconds, I was only here. At 3 seconds, I was here. 4 seconds, here. 5 seconds, here. And last but not least, we'll do 6 seconds here. One thing you'll notice is that it's not a best fit line. The points are not lined up perfectly. I can't get them to all be on the same line at any given time. So what I need to do is I need to draw a best fit line, a line that maybe looks like this. And the idea behind a best fit line is that the points that aren't on the line on this side, we want them to try to be the same distance apart as the points on the other side of the line. So perhaps in this case I can adjust the line somewhat, maybe to be like this. That's pretty good, right about there. So there's my best fit line, and it's showing me my position east as a function of time. And as a result, I would call this a position versus time graph. The next part of this tutorial that I'd like to go over with you is basically how to draw a graph in physics. So the very first thing that we want to do is we want to locate our origin or our beginning point, our reference point. And I'd like to do that always, whereby you are going 2 centimeters over and 2 centimeters up, and that from the white part of your page, and that becomes your origin. At which point now you can draw in your axes to the end of the page. So we'll go right to there, we'll say. And then your vertical axis, which will stop just shy of about a centimeter from the top of your page. So there's your two-dimensional axis. Now it's time to do some labeling. We want to know, well, what is this axis? And 9 times out of 10, it's going to be instantaneous time, so it gets a t, not a delta t. And the units in this case will be seconds. And then we start a convenient scale. So we start at 0 seconds, we'll say 1, we'll skip 2 and 3. So it appears that every centimeter represents 1 second. We'll just go to 12 seconds. All right? Now we want to label this vertical scale, and this is going to be our instantaneous position. So where are we exactly at any given instant in time? So I'll show you how I want you to draw this. I'll draw it horizontally, then I'll rotate it. So you simply write out, in this case, position, whose symbol is D. We can drop the vector symbol when we're dealing with a graph. First we're going to put a direction in meters to the, I'll choose east again. Then what I'm going to do is I'll just group these so they become one item, so I can easily move them. And I'm going to rotate that like so, and I'm going to make it just a little bit smaller so it fits nicely. And there is the correct way of labeling your vertical axis. Please note that you start writing from the lower left and you work up towards the upper left. All right, let's put some fictitious points on that graphs. So let's make it easy. We should label the scales. Let's just call it 1, 2, 3, and 4 meters. And very simply, at the 1 second meter mark, I was instantaneously at 1 meter. At this instant in time, I was at this specific location. At the 3 second mark, I was 3 meters east, and at the 4 second mark, I was 4 meters. So let's do that. Move that out of the way. I was at the 4 meter mark. That's going to be right. Oh, good. Okay, that's the 4 meter mark again. Well, in this case, it's fairly straightforward. It's just a distant line. All the point that's not the line, that's not the line. The line points all line up on one line. And now, in order to manipulate or to work with this, we'd like to find, well, at what rate is the position changing with respect to time? And so to do that, we find the tried and true method is to find the slope, as you learned in grade 9 and grade 10 math. This is called the run, as you know. And this is called, let's just choose, we'll choose green, and I'm going to get rid of the, arrow, if that will come up for me, and just if you want to do that, for whatever reason, so that's fine. We'll just ignore the arrow for now. Please note that you don't put an arrow there. Let's get rid of the arrow. And so here is the, hopefully you can see that all right. All right? So now, in order to convey information, because this is all about communicating, in order to convey information, I want to know what is this rise? Well, this is a simple one. Many will not be so simple. You simply put delta D is equal to, delta D is equal to D2 minus D1. Well, there's, right here, goes straight across, there's my D2. I started at home, and I went 4 meters to the east. So my second position is 4 meters to the east. Remember, the vertical axis is nothing more than a horizontal number line that you've learned in previous grades in math. D1 is very simple. It's my origin. I started at the 0 meter mark, so that's not hard. So delta D is then equal to 4 meters east, which is where you got to. So there's the rise. The run is done in a similar fashion. Delta T equal to the second time, take away the first time. In this case, the second time is the 4 second mark, and the first time is 0 seconds. So I'm going to do this, and there's the distributed property. The seconds goes with both. And I end up with 4 seconds. Now, a couple things to note. what I would like is I would like you to make sure that your calculation for the displacement is somewhere in the middle of the rise line, and similarly your run calculation should be as close as you can get without confusion to the run line. Now you're equipped to find the slope, because the slope is the rise over the run. So in this case we know the slope is the velocity. You can drop the vector symbol or not, doesn't really matter. It is the displacement divided by the time. Well, I know the displacement, it's 4 meters to the east. Please include the direction because, after all, it is a vector. And 4 seconds is a scalar, therefore v is equal to 1 meter per second to the east. The graph needs a title, and we'll title it D versus T. That is now instantaneous position versus instantaneous time. Again, when you see a D or a T, these are instants in time or space or a line. Whereas delta D and delta T are intervals of time or intervals of space or intervals between two positions. So from here to here. That would be a change in time, and it would be a change in one's position. So hopefully this little tutorial on graphing helps to solidify or clarify or simply help you out on doing graphs in physics.